Good afternoon, everyone. My name is Karen Truong, and I am an incoming second year at UCLA pursuing my BS in Computer Science and Engineering. And the project that I worked on this summer was the text classification of dbGaP studies for the pFinder project. My mentors for this project were Dr. Conway and Dr. Duan. So the overall goal of my project this summer was enhancing dbGaP's search functionality, a task that's been proven necessary because of the limitations that Raphael mentioned earlier. And my plan was to use text classification in order to produce better identification of relevant dbGaP studies and as a means of augmenting information retrieval in a way that was more focused on the topicality of the studies. In particular, my focus was on improving the classification of heart, lung, blood, and sleep studies, and today I'm going to talk about the steps that I took to do that, as well as the results I got. So let me begin by first giving you an example of the issue. This is a screenshot of one of the results that were returned from a simple keyword search of lung, and as you can imagine, the role of the gut microbiota in obesity in the Amish does not have much relevance to lungs, so there's a problem with the keyword search, and looking at the numbers in its performance, there was only 66% accuracy and a low level of precision. That means that a researcher would have to spend time and effort sifting through those results in order to retrieve relevant studies to his or her query. Our solution was to use machine learning algorithms to classify those studies and refine the information retrieval. In building my classifier, I used Weka, which is a collection of machine learning algorithms for data mining developed by the University of Waikato in New Zealand. And I built a classifier using 264 dbGaP studies that had been manually labeled by our domain experts at pFinder, Koei Lin and Mindy Ross. And we focused on 3 different algorithms, a C4.5 decision tree, naive Bayes, and a support vector machine, which tended to give us the better results of those 3 algorithms. Initially, I constructed a binary lung or not lung classifier, which was tested using 10-fold cross-validation. Some of the features that we use are common in text classification of unigrams or bag of words representation, which requires preprocessing of tokenization and stop word and punctuation removal. We also used bigrams, and then we wanted to use some features that were unique to dbGaP text, which prompted my next task of extracting features associated with dbGaP studies. I wrote a Python script to web scrape the study pages of all top-level studies in dbGaP for salient characteristics that we could use as features. For instance, mesh terms, funding agencies, associated journals, principal and co-investigators, and linked PubMed articles, which were accessed using the Entree programming utilities provided by NCBI. Some of our classifiers that we built would be just based off of mesh terms as features or a combination of these different feature types. For example, using unigrams, bigrams, and mesh terms within one classifier, or building another classifier where all the different features were used. And we were looking for the classifier that produced the best results in terms of F-measure and accuracy. The table on the left is a list of the 10 most frequent mesh terms associated with dbGaP studies. And if you look through those, you'll find that most deal with either the heart, the lungs, or blood. This is a word cloud that we generated using the text from some lung-related dbGaP studies. And you'll notice some prominent terms, such as nicotine, pulmonary, or smoking, that are indicative of lung and might be what a human would use as context to determine whether a study was lung-related or not. And so what we sought was to use this machine learning algorithm to help our classifier do something similar. Looking at the results, our classifier does outperform the free text search. If you recall, the manual keyword search of lung had an accuracy of 66% and a low F measure, whereas a classifier we built using mesh terms and funding sources as attributes had 95% accuracy and more than double the F measure of a manual keyword search. We also took a look at the 8 most discriminating unigrams that were chosen using chi-square feature selection, and you'll see some similarities with the terms in the word cloud. 2 of them are actually acronyms. The Exome Sequencing Project refers to a project to identify genetic variants in coding regions of the human genome that are associated with heart, lung, and blood diseases. And PLCO refers to prostate, lung, colorectal, ovarian cancer screening trials. But looking through that list, you can find that these are very lung-associated terms. So my project demonstrates that text classification is a promising approach for information retrieval, returning more accurate and relevant dbGaP studies than a typical keyword search. In the next few weeks, I will continue to work on this classifier, optimizing it by finding the best combination of features to use for a classifier, as well as the optimal number of features using chi-squared feature selection. And again, we're looking for the classifier that performs the best with respect to accuracy and F-measure. And we'd also have thought about adding some features such as MetaMap, which will map biomedical text to UMLS terms, and we'll move beyond lung into the other domains that I mentioned earlier of heart, blood, and sleep, and some more specific ones such as diabetes or lung cancer. We'd also like to expand our corpus simply because 264 documents is a relatively small data set to be working on, and we would like to prevent any possibility of overfitting our model. All of these steps are taken in order to develop a strong and accurate classifier that will hopefully be integrated into the phenotype discoverer system in the near future. I'd like to take this time to thank my mentors again for their insight, as well as everyone else who worked on the PFinder project, CalIT2 for hosting us today, members of IDASH and DBMI, and the NIH for supporting this internship. I've learned a lot over the past few weeks. It's been an incredible learning experience about bioinformatics coming from a computer science perspective, and also working in a research-oriented career with a team that has different sets of expertise and are coming from multiple disciplines. And I've also gained a lot of knowledge. I learned to program in Python just within this internship, and I got experience with NLP work, machine learning algorithms, specifically working with text classification for my project. And I also got some experience with some new tools to me, Weka and NLTK, and I still have a few more weeks here, so I'm sure I'll learn more, and I've taken so much out of this, so I appreciate everyone who has contributed to that. Thank you.